Right, we have one last talk before tea. So, John Walsh, Fundamentals of Faulting and the Pursuit of Failure. The floor is yours.
Thanks. I should say before I start that this is the work of many people, and in particular Hugh Anderson, and also John Moore, Sarah Blake, and Neil Grant. And just to look over my title, it's not the best it starts, is it? Fundamentals of Faulting and the Pursuit of Failure. Of course, the backdrop to that is that effectively that's what we chase all the time as the fault analysis group. We are actually pursuing failure, because for those of you who aren't geologists, and there may not be too many of you, but I'm assuming there are, the faults are the most important form of rock failure. They're accompanied with a displacement, and of course we all know, to people's detriment, of course, that oftentimes that can take the form of earthquakes. And from our perspective, as I mentioned, the happy coincidence is that faults are actually economically important. They can act as a locus for fluid flow. They can compartmentalize fluid flow. They can basically disrupt deposits which are economically useful. But from our perspective, they're just great structures. And in some ways, June Watterson used to say, he said, a fault is a poor man's shear zone. But you don't get much data in shear zones, so we just have to work with faults. This is a diagram which is from William Smith. He actually sketched it from work of John Strachey's in the coal measures. And you can see the coals here, and those coals are offset by this fault. It's a very wide fault. I'm not sure it's really that wide in reality, but they probably gave it short shrift and stayed well away. And that fault actually has a displacement on it, so it's down to the right. And it obviously disrupts the coal, and that's why William Smith was interested in stratigraphy. He was interested in structures. He knew that there are structures which offset his strata, the strata that he painfully looked at the fossils of, and he knew that they actually jumped across these weird things called faults, and I've made a living looking at them. He also knew, by virtue of his stratigraphy, that these faults were actually dead and buried before these sediments were deposited over the top. They had actually acted, they'd finished, and they'd stopped moving. So we can actually piece together not just what is economically important, how the shifts of coals through the areas such as Somerset or elsewhere, which is where he worked, we can also learn about process. Just to show you what one of these faults really looks like, this is very close to where we used to be in Liverpool. It was actually the first quarry we ever looked at, and it was the best quarry out of hundreds that we've looked at since. What are the chances of that? And this was near the capital of Ireland in Liverpool, and and it's a normal fault. The fault is 15 meters displacement, and the crust has been stretched in Carboniferous times. These are Carboniferous rocks. These are the sorts of rocks which William Smith worked on. They've been stretched in Carboniferous times to give us an overall extension of the crust. They're normal faults because they're normal. It happens that reverse faults happen in Wales, which apparently isn't normal. So these faults, they're there the world over. They do have damage. They do have fault rock associated with them because oftentimes, of course, they have earthquakes on them. William Smith had to contend with them, but he had something much bigger to concentrate on, and that was, as the father of English geology, so called, and rightly called, he produced the geological map of England, a thing of beauty. This is science, but it's also art. It's just fantastic looking, and it embodies so much that we've worked on since. Why did he do it? Well, he was actually motivated by predictions. He worked in coal mines, he worked in canals, but he was also agitated. He wanted to understand much more than everybody else exactly how these layers were deposited, and that he did. He worked out, if we take a vertical section through from Wales through to London, that he would end up seeing different layers of different age stacked one on top of each other, and they all had their distinctive paleontology and fossils about them. He actually revealed, by applied sciences, by defining solutions to problems, he actually gave us fundamental insights and mapping. In that sense, he was just a really good geoscientist. This was good geoscience. It wasn't applied, it wasn't fundamental, it was just good. and it was world changing. It changed the way we thought of it. Faults complicate his world, and he didn't shirk them, but we've spent our time looking at them. And this talk, I'm not going to talk about work that we've done over many years. I'm just going to talk in the last 5 years. And it's work which I think ties into what William Smith would have done, and he might have approved of. I'm going to look at the recent faulting of Ireland and Britain. I'm going to highlight mapping, new mapping. This isn't walking around looking at rocks, though I really approve of that, and we all do. It's looking at geophysics. So, and this is performed oftentimes. It's acquired by industry and government. I'm going to show that the distinction between basic and applied research is actually sometimes impossible to define. It's much easier to define the difference between bad and good science. So, here we are. This is a map of Ireland, where I began. The Carboniferous of Ireland is in light blue, and you see all these black faults. These are all Carboniferous faults generally. These are faults produced by north-south extension between 320 and 350 million years, sometimes probably a little later than that. And this is very similar to the very same faults which are developed here in Round Quarry. It's produced by north-south extension. You sort of think about why on Earth would you end up developing structures in this orientation if you've got north-south extension? And the reason is because you can't get away from inheritance. We have inheritance of structure. We've got underlying structure, which is Caledonian and older structure, which really has a huge effect on the following and the structures which develop later. These are heterogeneities which localize faults, and they actually generate a picture which in principle sort of looks very similar, where the faults are going the same orientation as these terrain boundaries. These are terrain boundaries in the Caledonian, and they curve around, they go east-west in Clew Bay. The new faults, these are newly developed faults. They know that that structure is there, that heterogeneity, that anisotropy is there. And that's why they're not perfectly perpendicular to the stretching direction. So what I'm going to do, I'll put on something which is not just a geological map. You can see these Carboniferous faults cutting through Northern Ireland. I'm going to show something which Mike Young, as the director of the Geological Survey of Northern Ireland, is actually led up and acquired. And this is aeromagnetic data. You can see it over the northern part of Ireland. It's since been rolled out over much of Ireland. This is the picture. This is showing total magnetic intensity. It's a marvelous picture. It highlights immediately the Antrim basalts, but it highlights all sorts of structures which are very interesting. And I'm going to focus in on those because they tell us about things that we never knew happened before. It's only in the last 5 years that we've actually defined these. So this is called the Telus Data Set, acquired by Mike, the GSNI, Geological Survey of Northern Ireland, and of course the BGS in 2007. Going to zoom into this area. You can see this area here. It's got all these stripes in it. These are actually showing tertiary dikes. These tertiary dikes, they actually intruded between about 55 and about 63 million years ago. They're relatively recent structures. We knew they existed, but we never knew they existed in such numbers. And they're cross-cutting Northern Ireland as they do. They go to Wales and so on and so forth. What's really interesting is these colors here, for example, they actually reflect reverse magnetic magnetization here of these dike systems. But you can see, I think, can you see that they're actually offset by structures coming across here? Yeah, see that? I'm going to show it a little bit detailed. So these dikes, they give us these kicks, these structures which are extending, these extended, filled in with basalt. And I haven't cut this, but you could. It just looks like somebody's actually cut a scissors through Northern Ireland. These are dikes which have been offset in the last 55 or so million years. It's probably about 60 million years. They happen to have intruded periodically at about the same time as some of these faults started moving. But the faults also actually extended into Oligocene times, 20 million years ago. Really recent activity. The movement on these faults, they're strike-slip faults here. For those of you who don't know what a strike-slip fault is, San Andreas is an example of a strike-slip fault. Unfortunately, it gives all faults a bad name. But these are much more interesting, and we're looking at ancient movements. These displacements are very large, we could never have guessed that 2.5 kilometers movement has happened on these structures so recently. This fault here, and they're sinistral. They're sinistral, so an anti-clockwise sense of offset. This fault here has 2.5 kilometers lateral offset. This fault here is 500 meters. And the most prospective shale gas basin in Ireland is just here. Yeah, this is Loch Allen. The geology in Loch Allen is really interesting. And that's what you probably don't want if you're actually generating shale gas. This is the Highland Boundary Fault. This is the Southern Uplands Fault. It's bracketed by two of the biggest and most famous faults in the world. But it's so interesting. You might want to steer clear of it for some purposes, though. So we're getting back. We're going to go into another area down the south. This here is the Newry Granite. Here are faults here, the Newry Fault and the Camlock Fault. Can you see these intrusions in the Newry Granite? Can you see that one is offset? Yeah. The offset is about 7 kilometers. Dextral. There's a dextral sense of offset. It's the opposite sense of offset on these faults. And this is all recent. These faults have been active. Most likely, this fault movement is actually closer to Oligocene in age. So the last few tens of millions of years. We knew this from maps. And so Smith would not have been surprised that you can map the offsets here. But of course, the clarity given by this magnetic data, why was the magnetic data acquired in the first place? I think I'm right in saying, though Mike can correct me, that a lot of this was to try and get companies to come into Northern Ireland and explore for minerals. So this was an economic push. But you see that it's actually come up with some really interesting academic findings. And when we put them all together, what we get from the faults that we can see from this data set, they look like a conjugate pair. They look like the sorts of things you see in your first year experiments. This has moved dextrally, that sense, and this has moved sinistrally. And the way, oh sugar, I'm moving away from this and I realize nobody has a clue. Sorry about that for those of you who are actually viewing on film, on television. I better behave myself. I knew I needed to be nailed down. So, and the way to produce that is by compressing roughly north-south. If we compress roughly north-south, we can produce faults like that. And this is why I refer to it's alpine Pyrenean compression. What it is, and this is a map for the Oligocene, not for the Paleocene, which is slightly different, and that actually gives us an evolution of the activity of these different faults. They sort of swap their activity. But in the Oligocene times, you can see that there's a north-south compression arising from Africa, migrating northwards. There also was an anti-clockwise closure of the Pyrenees here a little earlier, mainly, and this all put Ireland under a squeeze. It ended up in a vice, and it ended up producing these strike-slip faults, which we never knew existed. Now, I'm going to look down a little bit more, further south, to 10 kilometers from the house I used to live in. I was brought up in a lower Paleozoic world, maybe Paleozoic, but you couldn't see the rocks. So, and what we found through, and this is a different type of mapping, this is seismic mapping. Companies have acquired this to look for oil and gas, though for the reasons that these structures are in there, these recent structures, they didn't find oil and gas, I suspect, because it's leaked off. But they found great geology. These faults here are big normal faults, most likely Carboniferous. This is a top Westphalian map. 5 to 6 kilometer displacement. These are whoppers. And those faults here, who would have thought that a cross section, I lived there, and a cross section, I came back 20 years later and still live there. And this cross section shows a huge normal fault. These are fantastic structures. Green is down, red is up. But it's cross-cut by this strike-slip fault, the Codling fault. 9 kilometers displacement. Who would have thought? Nobody ever told me that in lectures. Nobody even told me that a fault with Jurassic in its hanging wall actually extends into Ireland and bounds the Leinster granite. It's not been published. I think it's right. This is a 3D model. Looks fancy. These faults extend along the Leinster granite, these big old faults, Carboniferous faults. But this Codling fault, the recent one, is there. We can look at outcrop data. Seismic is some resolution. God, I need to be nailed down again. Seismic is reasonable resolution, but outcrop is better. See all these north-northwesterly faults? They're all dextral. Ireland is cross-cut by north-northwesterly faults, all tertiary and all really transmissive. So much of the water in Ireland is actually generated from these structures. We didn't even know they existed 5 years ago. So this is our map of Ireland, slightly souped up. We put in these bold faults, which are actually active in the tertiary times, and that's our aeromagnetic data. This is our seismic data. This is seismic mapping. It's not geological mapping, but it's new seismic mapping. That's aeromagnetic mapping. Just as these are sort of high-tech versions of what Smith would have done. These faults cut down, and now we know that these basins, they go onshore Ireland. We get little sort of clips of them. But what about England? What about Britain? Well, we can go onto it in the Menai Straits, one of the more famous faults in Britain. Anglesey here, and these are older magnetic data, and you could see we've got hundreds of meters, if not kilometers, of offset of tertiary dikes. Now we've actually got a basis for explaining these are conjugate systems. These particular faults are pre-existing, and they're reactivated as sinistral faults. These ones are brand new. They've just formed. They don't localize on pre-existing structures, so we get a swathe of them covering Ireland, and they're very important for groundwater flow, probably for hydrocarbons too. So I'm going to finish off. This is the Carboniferous Basins, the ones I've been referring to, the Carboniferous Basins, which are not very well shown on this particular sketch, but there are many and varied here. They come around the Midland Craton. They curve into the North Sea, and we end up with a lot of these basins developed within seismic data. And those particular faults are within this sort of band of Carboniferous basins. A lot of this is uplifted, or we don't know have the definition of it here. This band of Carboniferous basins, and we forced it, we know in tertiary times, north-south. When that happens, these move sinistrally, yeah? But these move dextrally, and we know that. And now we've actually got data which says that north-northwesterly dextral faults develop in Ireland, but northeasterly faults, newly formed ones, developed in North Sea. These faults were called De Keyser faults because it's named after a fella called De Keyser. And De Keyser never published a paper on it, but in industry, people have talked about De Keyser faults. And we believe these are, as many do, these are tertiary faults, but they are the perfect symmetry about the Midland Craton. We get a system which has partitioned, localized faulting along the pre-existing faults and newly formed ones. This is seismic data in the Salt Pit Basin, the main big faults pre-existing, and look at these lovely little faults which are newly propagating, developing across it. This is in a mine in Ireland, in Lachine, and this fault here is about 5 meters displacement. It produced water which was at a rate equivalent to 15% of Dublin's daily water usage. These faults are very prone. They're open, they developed at shallow depths because they're only recent and they're not filled in, so they flow a great deal. But I should show you a diagram that we actually produced 2 weeks ago, and it's from just down here. And this is from seismic data, 3D seismic data in Ireland, offshore Ireland. Look at that, the pre-existing faults coming through here, and then these later northwesterly faults transacting through Ireland, the perfect symmetrical pair of across the Midland Craton. So I conclude and suggest that ancient faults exercise a major control on crustal deformation. There's nothing new in that. This is just an example, I think a nice and recent example of it. Tertiary deformation and faulting can be reconciled across Britain and Ireland, and there's a really sensible pattern to it. But these faults have significant impact on fluid flow. I didn't mention that the De Keyser faults can compartmentalize reservoirs, or they can make them work, depending on the rocks within which they're contained. So mapping for economic purposes can provide fundamental insights. And I think William Smith would approve. Thanks.
Good, we've got time for a couple of questions. Yeah, Peter.
Excellent stuff as well, John.
Thanks, Peter.
Remember the days at Liverpool very well.
Oh, I remember too.
Spent a long time looking at induced earthquakes, induced by various things, but most recently induced by fracking.
Yeah.
And the question we've been asked is how close can you be to a fault and frack without stimulating in a way which actually might produce an induced seismic event of some size? And that's a difficult question, because you're kind of telling me that it's pretty difficult to escape faults on any scale through here. How might we try to characterize that relationship between pressure changes in fracking and the instability of these faults? Because after all, a fault just stops to move because there's only infinitesimally less stress than there was before. Yeah. Is the UK a place where you could ever actually put numbers on that?
But what we used, if you remember, is we used coal measure data. We spent 20 years acquiring coal measure data, mine plans, to generate really high definition maps. And it's true to say it's very hard to avoid faults. In fact, at one time, I often wondered whether they put in nuclear power stations just to actually locate the faults. Because every nuclear power station had a fault in it. And I think there's a message in that. I mean, a geological fault in it. There's a message in that, is it's really hard to avoid faults like that. And then it comes down to scale. I mean, if you want to induce a seismic event on a particular fault, then its source radius and the scale of structure is important. So you want to avoid big structures, which potentially could localize very big single earthquakes. But I mean, as is shown in Cheshire and Blackpool, the example, the fracked example, this was not a very big fault. And when you get a magnitude earthquakes, which are so small, I think it might be about 100 meters in length. If it's 100 meters in length, then the fault might end up having a displacement of 1 meter. I mean, most sedimentologists wouldn't even see that. You know, they'd look at the sedimentology and they'd skirt through a fault which is 1 meter. It's so insignificant. So I'm actually obviously really irritated, some sedimentologists there. but you know, they don't see our faults, I don't see their sediments. So
I guess we've been asked to actually have thresholds of seismicity which are much lower than I would potentially thought were problematic.
Yeah.
But the government kind of backed away and said 0.5 magnitude. 0.5 is a very small earthquake to have to try to avoid.
Yeah. I don't think you can avoid it. I think what's important is that, well, even a magnitude 2 or 3 is really very small. And there are people living in Galway who have lorries going past their front house, which is generating more of a shake than that. So, no, I think it has to be sensible that, you know, when you say 2 or 3, this is very low, but 0.5 hardly registers. I don't think there's a rock that doesn't contain a potential surface which could move with for a magnitude of 0.5. So maybe an orange light. And I should say that in our country, in Ireland, our geology, where the potential shale gas is really complicated and very interesting. And like the Chinese, they wouldn't wish upon you living in interesting times. Where shale gas is concerned, you don't want to live in interesting geology. And I think Ireland is perhaps really challenged by that. I think in the UK, nothing that I've said actually has anything pertinent to say about the UK. But there are these tertiary structures, and I think they're as well to remember, because it seems to me that they're really quite common, and the more we look for them, the more we find them. So, yeah.
Question at the back. Brian.
Do I need the microphone? Thank you, John. If we go to classic William Smith territory, southern England, yes, using Smith's techniques, you conclude that there was vertical uplift at the end of the Cretaceous, and then there was compression pretty much at the time you're suggesting, the compression that gave you a conjugate set of strike-slip faults there. Is that what we're seeing in Ireland? Is that what you're talking about there too?
Yeah. what's nice is that in offshore Ireland, when we look at seismic data, we can see fantastic buttressing of hanging walls, which are actually tertiary related. In much the same ways you can see structures like that in the Bristol Channel, there are classic inversion-related anticlines arising from tertiary movement. But equally in the Bristol Channel too, there are very large strike-slip faults, which are actually relatively recent as well. So yeah, I think we felt one and the same sorts of pressures, perhaps not as strongly felt in Ireland. Actually, what we find is that as we migrate further westwards, perhaps because of the anti-clockwise movement of Iberia, the actual amount of compression tails off gradually as you go towards the west. So, but I think they are very similar. But the actual compression kicks in probably late Cretaceous, early tertiary times. Then it looks like there's a quiescence, and then it kicks in later on. So yeah, we think they're the same.
You've actually got evidence of crustal shortening early Cenozoic.
Yes, yeah.
Because there isn't in England. It's a good old geological myth that there is, but you can't actually measure it. It's so slight.
Yeah, that's the thing.
The seafloor came up because it was lifted up vertically, not because it got a push from anywhere.
Yeah, I mean, we're lucky that whatever compression exists has been localized on discrete structures, which we happen to have fantastic magnetic data across. If those discrete pre-existing structures didn't exist, then it would look like a little push. It just wouldn't look that significant. And it's actually overwhelmed by the uplift related to the plume, the Icelandic plume, which is in central Irish Sea. So no, actually that's where faults are a good thing. They concentrate displacement, and if we're lucky enough to measure it, then we're in business.
Good. Last question if there is one. I saw a hand earlier on. Oh, yeah, go on.
As a continuation on the previous question then. So those of us that sort of do teach sedimentology in Dorset, when it comes to structures, we always blame everything on the Alps. But at the back of our mind, there's always been this issue that there's not much deformation as we go across the channel into Europe. So does it come down to purely being due to where the Hercynian front is that is controlling all of the evidence for compression that we see in the Cenozoic, both in the evidence you showed and the evidence we see in the Mesozoic in Dorset?
Yeah. Yeah, I think that, I mean, really, when you apply compression, the rocks feel stress. And whether that stress is actually reflected in strain, which is fault displacements, depends on what's there already. And I think if you look at the alpine deformations, there's a lot in the Alps. It just happens to be localized in particular areas, which are slightly different to Ireland. I mean, what surprised us is that, yes, we don't have much of that deformation, but we still actually feel it. And we still see it, but the strains are very much lower. What surprised us is that it's actually quite a long way north in Ireland. And of course, those structures, if you go to the Inner Moray Firth along the Great Glen Fault, you can see strike-slip movement. We used to suggest it was something else, but it's almost certainly tertiary movement. And it's on kilometers scale. So I think it's just a matter now of us actually hammering down how much strain there is. But it's as well to remember there are hundreds of kilometers, perhaps even 1,000 kilometers from where the shove is coming to us. So the amount of strain is not great, but then it's all relative. If you're sitting on a fault, that's not good. Yeah.
On that note, I think I'll bring it to a close. Thank you very much.